Hello, we will begin our Unit 3 with a discussion on wave motion. Now, wave motion is the motion of something. Now, what is moving in wave motion? Wave motion is actually the transfer of energy from one place to another through a medium. What is a medium? Air is a medium. Water is a medium. Well, the stick I'm holding is a medium. Well, I can show you another medium. You can see this is a stretched spring that I'm holding. Now, watch what happens when I give this stretched spring a brisk. Well, what I'm going to do is give this stretched spring a. Now, can you see anything that happens? I'm going to pull it up slightly. Well, what is actually happening is the energy is moving. Now, the motion of energy, let me show it to you over here. Now, if I pull one end like this, what you notice is the pulse that I generated. Now, I'm generating a pulse. What I'm doing is making this segment of the string to move up and down. When I do that, you notice that that pulse gets transmitted right along the length of the string. Now watch again. Now this is actually an example of wave motion. The energy I create at one end of the spring by setting this end into up and down vibration is passed on from segment to segment of the spring so that it travels to the other end. Well, that is a wave motion. Alright, so if you tie one end of a rope like this to a fixed end and stretch it and pull it by giving a little jerk on one end. Give it a little jerk on one end and see what you observe. You see a pulse moving along the length of the rope. Now, when the pulse reaches the support, it gets reflected. Now, here is the way the pulse is generated. Now, you can see each part of the rope gets the energy a little later. So if you see the pulse here now, a little later the pulse is here. After a little while the pulse is here. The pulse advances to the right. It is the energy that advances along the length of the rope. So the jerk sets the segment of the string close to your hand into an up and down vibration, and that up and down vibration is passed on from segment to segment until it reaches the end of the rope. The energy of the jerk gets passed on from segment to segment due to the elastic properties of the string. You see, each segment is attached to the next one. So when you set one segment into vibration, that energy gets passed on to the next one. And when that begins to vibrate, the energy gets passed on to the third one. So the energy gets passed on from segment to segment. But one thing you notice there is the first particle begins to move. The second segment begins moving a little later, and that is why you see the pulse advancing. You see, a pulse is the up and down motion of the segment. A segment over here moves up and down a little later than the segment here. So you see the pulse here now, a little later the pulse moves over and over, it continues. So the rope segments do not really move along the rope. You see, the segments of the rope do not move away from its place. Well, if you look at that again, this is our rope or the spring. Now, if I pick on one segment here, that segment simply moves up and down. See what's the motion of that? The segment simply moves up and down, and that motion is passed on from segment to segment. So what is actually moving? What is moving is the energy. It is the energy that is moving. Now, this is wave motion. So the segments simply vibrate up and down. The energy of vibration travels the length of the rope. Each segment of the rope is set into vibration a little later than the previous segment. That I explained to you. Each segment, the next segment gets the energy a little later than the previous one. That means all these segments are not vibrating together. When the first segment starts vibrating, the next one starts a little later. The third one still later. The fourth one even later. So there is a lag in their vibration. And that is that lag that creates the pulse that advances along the length of the rope. So the vibration of each segment of the rope is similar to the vibration of a loaded spring. Now, how does a loaded spring vibrate? Have you seen a loaded spring vibrate? Now, here I have a loaded spring. In other words, that is the spring, and this is the load I'm going to suspend from it. And if I pull the load and leave it, you see this load vibrating? Now, the segments of the string vibrate exactly like the vibrations of a loaded spring. This is the kind of vibration that the spring segment also has. Now, this vibration is handed over from segment to segment, the vibrations of the loaded spring. Now, if you create a wave in water, well, drop a stone in a pool of water, you see the water will begin to move up and down. You see, something you put on the surface of water will show you how the water particles move. The water particles simply move up and down. The energy of motion will advance. You see, the wave profile you see is due to the fact that every particle in water will vibrate a little later. And that is how a wave profile is created. When a pebble is dropped into a pond of water, the pebble sets the molecules of water into up and down vibration the same way as the loaded spring will vibrate. And we call that oscillations. Oscillations are the up and down motion. Now, as the energy reaches each molecule, a little later, the displacements of the molecules will be different in time. So, if a molecule here has reached all the way to the top, the energy of motion for a molecule like this has taken it to this position. So what you see here are positions of the particles that are in vibration. Now, each subsequent molecule will be in a slightly different phase of vibration. Now, if you look at many particles in the medium, if they all vibrate together, can you imagine all of them moving up and moving down together? Now, that will not create a profile like this. Now, what happens is, each particle has a different phase of vibration. Now, what is the meaning of phase of vibration? I will illustrate that in a second. Now, each subsequent molecule will be in a slightly different phase of vibration. And it is that different phase of vibration that makes the surface of water looks like ups and downs. You see, when you have an up portion, that is where the particle is moving up. When you have a low portion, that is where the water molecules are moving down. So you have the ups and downs created in a wave. So it is this progressive phase difference that gives the rise and fall of a wave profile. A wave profile has the rise and the fall. Okay. Now, putting all these things together, we can now define wave motion. What is the definition for wave motion? So, we can define wave motion as a kind of energy transfer. So, wave motion is a kind of energy transfer in a medium. In other words, a wave motion can take place in air. Air is a medium. Wave motion can take place in water. Water is a medium. Wave motion can happen in a spring. Spring is a medium. So, a wave motion is a kind of energy transfer in a medium due to the vibrations of the particles of the medium. You see, a disturbance created at one part of the medium will set the particles of that medium into vibration, and the energy of vibration will then be propagated along that medium. Wave motion is a kind of energy transfer in a medium due to the vibrations of the particles of the medium without the particles themselves moving away from their positions. You see, a particular particle will simply move up and down, and the energy of motion gets transferred from particle to particle, and the particles themselves will not move away. And that is what we call wave motion. Let me see if I can show you a couple of illustrations of wave motion. Now, watch these three illustrations of wave motion. In the first example, we have a number of students are holding hands and standing in a line. Now, if you give an up and down jerk to the first student, that energy gets transferred from the first student to the second student to the third to the fourth, and see how the profile gets created. You see? Now, watch how the phase of motion changes. Are they actually moving in phase? What is the meaning of moving in phase? Now, watch these two particles moving. I can make these two particles move in phase. They move exactly together. They are in phase. But the motion of these students, are they in phase? This one starts, and a little later the second one starts. The third one starts even later, the fourth one, and so on, and you can see the wave profile created. So what happens here is the individual students simply vibrate up and down. The energy of vibration is passed on in that medium. In the same way, here you have a lot of particles in this medium. When you give a push on the left side, here the particles are set into vibration, and the vibration is passed on from one end to the other. If you watch carefully, what's the particle I'm pointing? Now, did that particle move away? No, that particle simply moved back and forth. And look at the pulse I created on a string. The pulse created here moves along. Why? Because the energy of the pulse gets transferred to each particle a little later. So here we have good examples of wave motion in a medium. Alright, so let's move on and talk more about wave motion. Now let's now talk about period and frequency of a vibrating particle. Now remember, a wave motion is created by particle vibration. Vibrations of the particles that make up a medium. Therefore, some of the information about vibration of particles is important for us. Now here I have a particle, I'm going to set it into vibration. Now what is the meaning of period of vibration? Now look at this one now. When it starts here, it is pulled down to a lower extreme, then it comes back, it goes to an upper extreme, and then comes back. It means this particle has now completed one vibration. Now, watch that one vibration one more time. It goes down, comes back, goes up, comes back. That is one complete vibration. Or I can start like this. It goes up, comes back, goes down, and comes back. This is one complete vibration. Alright, watch that one more time. Let's call this the equilibrium position. Now this is the normal position of the particle. When this particle is disturbed, given some energy, what's going to happen? It's going to vibrate. It goes up, comes back, goes down, and comes back. This is called one complete vibration. The time taken for one complete vibration is called the period of vibration. The time taken by a particle to complete one vibration is called the period. And we're going to represent the period by the uppercase T. And the period is measured in a unit second. Alright? So you understand the meaning of period. The period is the time taken for one complete vibration. It is represented by the uppercase T, and it is measured in seconds. What is the meaning of frequency? Frequency is how frequent does it happen. Now, this object vibrates. Now the question is, how many times a second does it vibrate? If I count the number of times it vibrates in 1 second, frequency is the number of vibrations per second. The number of vibrations of the particle in 1 second is called its frequency. And now frequency is represented by the lowercase f, and we measure it in a unit called hertz. Hertz. And we write uppercase HZ, not just H alone. Hertz is written HZ. So make that correction there. It must be HZ, not simply H. Frequency is represented by the lowercase f, and we measure it in a unit called hertz. What does hertz mean? Hertz means per second. So if I say the frequency of this is 5 Hertz, what does it mean? The frequency is 5 Hertz means it goes up and down 5 times a second. It does 5 complete vibrations in 1 second. That is the meaning that the frequency is 5 Hertz. Alright. Now, if a particle vibrates 5 times a second, what is its period? Alright? If a particle vibrates 5 times a second, its frequency is 5. Is that right? Its frequency is 5 Hertz. Now tell me, if a particle vibrates 5 times a second, what is the time taken for 1 vibration? Can anybody tell me? Now, this completes 5 vibrations in 1 second. Alright? What is the time taken for 1 vibration? Well, the time taken for 1 vibration will be 1/5 of a second. Is that right? If the particle completes 5 vibrations in 1 second, the period, the time taken for 1 vibration will be 1/5 of a second. Now, if the frequency is 10 Hertz, if it goes 10 times a second, then the period will be 1/10 of a second. Well, I hope that is understandable. Well, a particle that completes 5 vibrations in 1 second will complete 1 vibration in 1/5 of a second. That means if the frequency is 5 Hertz, the period will be 1/5 of a second. Now, can you tell me how period and frequency are related? If the frequency is 5 Hertz, then the period will be 1/5 of a second. If the frequency is 10 Hertz, the period will be 1/10 of a second. If the frequency is 2 Hertz, what will be the period? Will be 1/2 of a second. That means the period T and the frequency F are related such that, anybody tell me what is that relation? One is the reciprocal of the other. That is T equal to 1/F. Period equal to the reciprocal of the frequency, or frequency equal to the reciprocal of the period. Or we can say one is the reciprocal of the other. Period is 1/the frequency, or frequency is 1/the period. That means if you multiply the period and the frequency, it will be always 1. That is what it means. Okay, I promised you some time ago that I will illustrate the concept of phase and phase difference. Now, what is the meaning of phase and phase difference? Now, suppose I have 2 objects. I showed it to you some time ago. I have 2 objects, and I'm going to show you how they are going to vibrate. Now, look at the vibrations of these 2 particles. Now, watch how they move. Now, they are moving actually in phase, or we say they are in step. Is that right? So, in phase means in step. Now, when the particles move like this, that is, when the particle on the left moves up, the particle on the right also moves along with it. So, this is motion in step. Then we say the particles are in phase. So, here we have 2 particles. Particle 1 and particle 2. They are going to be moving together. So what will be their phase? Let us consider several particles oscillating between two extreme positions. Now, what is the meaning of oscillating between two extreme positions? Now, I told you when I showed you this spring oscillating. Now, this is its normal position. What did we say we're going to call that position? We call it the equilibrium position. Now, when it is taken to an upper extreme, it comes back to the normal position, then it goes down to a lower extreme, it comes back to the normal position, completing one vibration. So a vibration happens between an upper extreme and a lower extreme, right? So consider a set of a number of particles oscillating between two extreme positions. Now watch it again to understand those extreme positions. Normal position, upper extreme, back to the normal position, lower extreme, back to the normal position. That is one complete vibration. So what does one complete vibration made of? From the normal position, you go to the upper extreme, back to the normal position, lower extreme, back to the normal position. That is one complete vibration. Okay. Now particles 1 and 2 are at the normal position. We call it the equilibrium position. And they are both moving up. That means they will both reach the upper extreme together. They will both come back to the equilibrium position together. They will both reach the lower extreme together. And they will come back to the equilibrium position together. We say they are in phase. Just like soldiers marching. Have you seen soldiers marching? Each one is in phase with the other. When the sergeant says left, everybody's left foot goes forward. Right, everybody's right foot goes forward. Is that right? So soldiers are marching in phase. If one soldier goes out of phase, the sergeant can immediately see it. Alright. So these two particles, 1 and 2, are both in the same phase. There is no phase difference. There is no phase difference between the two particles. They are completely in step. Alright, look at particles 3 and 4. Particles 3 and 4 vibrate like this. Okay, now if you can watch my little red balls here. Now, whereas one particle this is going to go, well, this is going to go up and the other one is going to come down. Now, that means I have one on my right hand. This is my right hand particle and this is my left hand particle. Now, when my right hand particle begins to move up, my right hand particle is beginning to move down. Now that means the right hand particle has actually completed the up and down motion. It is now beginning to go down. That means, I want you to watch this very carefully. What happened is, the particle on the right, the particle in my left hand has actually completed half a vibration. The particle on my left hand has actually completed half a vibration when the particle on the left begins to vibrate. Or we say this particle is ahead. Particle 4 is ahead of particle 3 by half of a period. Now remember, a period is the time taken for one complete vibration. So this has gone up and come down. The time taken to go up and come down is half a period. So this particle 4 has actually completed half the vibration when particle 3 begins to vibrate. So while particle 3 is beginning to move up, particle 4 has completed half a vibration and is beginning to move down. Can you tell me what is the phase difference? We say there is a phase difference of half a period. What is the meaning? There is a phase difference of half a period. Means particle 4 is half a period ahead of particle 3. That is the meaning there. So particle 3 has to go to the upper extreme and back to catch up with particle 4. But by the time particle 3 does that, particle 4 goes to the lower extreme and comes back. You see, that means particle 3 is always trying to catch up with particle 4. Particle 4 is ahead of particle 3. By how much? By half a period. So by the time particle 4 would have actually gone down and back. So they are always moving in opposite directions. So is it reasonable to say that particles 3 and 4 are always out of phase? When one begins to move up, the other moves down. You see that? They are completely out of phase. One particle leads the other by a period of t by 2, period of half a period. So what is the phase difference between particles 3 and 4? Now particle 4 is half a period ahead of particle 3. Did you really understand that? Particle 4 is half a period ahead of particle 3. That is, when particle 3 begins to go up, particle 4 has completed its upward journey. It has gone up and has come back. So when particle 3 begins, particle 4 has completed half of the vibration. That means the phase difference is half of a period. We say particle 4 is half a period ahead of particle 3. Okay, in that case, can you look at particle 5 and particle 6? Tell me, what is the phase difference there? Particle 5 is beginning. Particle 6 has gone all the way to the upper extreme. Now, you must understand, if this is the normal position, alright, this is the normal position, you go to the upper extreme, back to the normal, go to the lower extreme, back to the normal. Tell me, if the time taken for that complete journey, that is the normal position, you go to the upper extreme, back to the normal, lower extreme, back to the normal. The time taken for this is one period, we call it T. What is then the time taken just to go up? The time taken for just to go up is a quarter of a period. So you can say particle 6 is now gone all the way to the upper extreme. It has been vibrating for quarter of a period when particle 5 begins. That means this particle 6 is ahead of particle 5 by a quarter of a period. Now, what is the phase difference between particles 5 and 6 therefore? The phase difference is a quarter of a period. In that case, can anybody tell me what is the phase difference between particles 7 and 8? Now, my offer of the extra credit is going to come back. I'm going to give you 2 extra credit points for anybody who can write and tell me what is the phase difference between particles 7 and 8. In other words, when particle 7 begins, what part of the vibration has particle 8 completed? Alright, so tell me, what is the phase difference between particles 7 and 8? Write to me and you can earn your 2 extra credit points. Okay, let's move on. Now, you now understand the meaning of phase difference. If the 2 particles or any number of particles are all vibrating in step, they are all in phase. But if they are out of step, there is a phase difference. Okay, now I have chosen 5 particles of a medium. Now, what does that mean? 5 particles of a medium are similar to 5 segments of this spring. Alright, first segment is particle 1, second segment is particle 2, third segment is particle 3, and so on. So I have taken these 5 particles just like the 5 segments of the string, and I'm going to set these particles into vibration so that energy gets transmitted along the medium. Alright. Consider 5 particles of a medium oscillating with a phase difference of a quarter of a period. What is the meaning that the phase difference is a quarter of a period? Well, try and understand this. Phase difference is a quarter of a period means when the first particle starts vibration, when it completes a quarter of a vibration, the energy will just to reach the second particle. So the second particle will begin only after the first one has completed a quarter of a vibration. That is the meaning. The phase difference is a quarter of a period. When the second particle begins to vibrate, the energy will reach the third particle after a quarter of a period. When the third particle begins to vibrate, it will take a quarter of a period for the energy to reach the next particle. That is the meaning. We say the phase difference is a quarter of a period. Okay, so if the phase difference between successive particles is a quarter, you must correct, this is not T by 2 but T by 4. So if the phase difference between successive particles is T by 4, could you please correct that? Small error there. It is not T by 2 but T by 4. Now you can see my correction will disappear when I go to the next line. So you must make that correction in your notes. So if the phase difference between successive particles is T by 4, it means as the first particle vibrates from its normal position and it reaches the upper extreme, the energy will just to reach the second particle. So as the first particle completes 1/4 of a vibration, 1/4 of a vibration is from the normal to the upper extreme. The energy reaches the second particle. Okay, let's see, let's make that drawing. So here, the first particle is now sitting at the upper extreme and the energy has now reached the second particle. Alright, the first particle has completed a quarter of a vibration and the second particle is now beginning to vibrate. Okay, so the situation is the first particle. Now, tell me what happens after another quarter of a period. After another quarter of a period, the first particle from the top has come back. You see? And the second particle would go a quarter of a vibration up. And the energy will just reach the third particle. So you can see when I color them red, that is their current positions. Particle 1 has completed now half of a vibration. Particle 2 has now completed a quarter of a vibration. And the energy has now reached the third particle. Now can you tell me, what will be the positions of these particles after another quarter of a period? After another quarter of a period, the first particle will now go down to the lower extreme. The second particle will come back to the normal position. The third particle will go up to the extreme there, and the energy will just reach the fourth particle. Is that right? Alright. Let's write that. After another quarter, that is, after 3 quarters of a period. After 3 quarters, watch it again. The first particle has gone up, comes back, and one more quarter, it is going to be here. After 3 quarters of a period, the first particle is going to be here. Where is going to be the second particle? The second particle has completed up and back. Where is going to be the third particle then? It is going to be up there, and the energy will just reach the fourth particle. Now look at the profile of the wave. This is how the wave begins to take shape. The particles of the medium are at different phases of their vibration. Can you tell me now, what will be the positions of these particles after another quarter of a period? Anybody tell me? Well, after another quarter means after one full period. After one full period, particle 1 has completed its vibration. It has come back to the normal position. So particle 1 has completed its one vibration. Alright, where is particle 2? Particle 2 has gone all the way down here. Where is particle 3? It has completed half the vibration and has come back to the normal position. Where is particle 4? It has gone all the way up, and the energy just reaches the 5th particle. And look at the profile of the wave now. You see the first particle here, the second particle here, the third particle here, the fourth one here, and the 5th. You can see the wave profile. Why? Because each particle vibrates in a different phase. Now you have a complete wave. So now this particle is beginning to go up, and the 5th particle is also beginning to go up. That means the first particle and the 5th particle are now going to be in phase. Is that right? Yes, the first and the 5th are going to be now in phase. So particle 1 and particle 5 now begin to move up at the same time. And therefore we say these two are now going to be in the same phase of vibration. So now between the two particles that are in the same phase of vibration, we have a full wave now. You see, a full wave is defined as the wave that is in between two nearest particles that are in the same phase. Alright, so by the time particle 1 completes one vibration, watch this again. By the time particle 1 completes one vibration, where is the energy reached? The energy has reached the 5th particle. Now, the distance advanced by the wave in a time of 1 period. Now, what is 1 period? 1 period is the time taken by the particle to complete one vibration. By the time particle 1 completes one vibration, that is 1 period. And during that period, the energy advanced all the way to the 5th particle. Now, we are now going to define a quantity called wavelength. A wave has a wavelength. What is the definition of wavelength? Wavelength is the distance advanced by the wave by the time particle 1 completes one vibration. In other words, wavelength is the distance advanced by the wave in a time of 1 period. You see, the time taken by the particle to complete one vibration is its period. And during that time, the wave advanced this distance. The wave traveled this distance. And that distance is what we call the wavelength. Now, we represent the wavelength by the Greek letter. I know most of you are not very familiar with Greek letters. We will use a couple of those. Now, you read this letter as lambda, lambda. And we represent the wavelength by using the Greek letter lambda. So, if I ask you what is that wavelength, it is the distance measured from the 1st particle to the 5th particle. Why? Because by the time the 1st particle completes one vibration, energy reaches the 5th particle. So this distance is what we call one wavelength. So wavelengths can also be defined as the distance between two nearest particles that are in the same phase of vibration. You see, particle 1 and particle 5 are in the same phase of vibration. Therefore, the distance between them is one wavelength. But it is much more useful for us to take the first definition. What is the first definition? The first definition is wavelength is the distance advanced by the wave in a time of 1 period. Alright, don't forget that. Okay. Now, let me see if I can show you an illustration. Now, here I have a particle that vibrates. Now, by the time this particle completes one vibration, the distance advanced by the wave is one wavelength. You can see a wave can advance to the right or to the left. I'm going to set this particle into vibration. Watch the animation and see how the wave moves to the left. Now, watch this one. The particle is vibrating up and down, one complete vibration. And wave. This is a full wave. Now, the particle has completed one vibration. The wave advances by a distance called one wavelength. Okay. Let's now obtain a relation connecting wavelength, frequency, and obtain the wave equation. Now, you must be familiar with the wave equation. Now, I remember in the last class, I told you that I taught you the wave equation already. That was not true. We are only going to see it now. Alright, so pay attention and learn about the wave equation. A wave equation is an equation that gives you a relation between wavelength, frequency. What is frequency? Frequency is the number of vibrations per second of each particle. Now, each time a particle completes one vibration, a full wave is produced. And so frequency can also be defined as the number of waves produced per second. The number of waves produced per second is the frequency. So we can use the definition of wavelength to get an equation of the wave speed. Alright, can you tell me what the definition of wavelength is? What is the definition of wavelength that we had? Well, our definition is wavelength is the distance advanced by the wave during a time of one period, right? So if v is the speed of the wave, you know how speed is defined. Speed is distance divided by time. Is that right? Yes. So v, the speed, is distance divided by time. Now let's go over here. When the distance traveled by the wave is one wavelength, what is the time taken by the wave to travel one wavelength? The time taken by the wave to travel one wavelength is the period. So I can now call it, if this distance is the wavelength, then this time will be the period. So the wave travels a distance of one wavelength in a time of one period. So I can write v, the wave speed, equal to distance. Distance is the wavelength and time is the period. V equal to lambda over t. Is that simple? Is that right? Now look at the way I'm going to write it. I'm going to write it as 1 over t times lambda. Is it okay? Lambda divided by t is the same as 1 over t multiplied by lambda. Now, why did I write like that? Because 1 over t. Now, do you know the relation between frequency and period? We talked about that in the beginning of the class. Frequency is the reciprocal of the period. In other words, 1 over the period is equal to the frequency. So I'm going to replace this 1 over t as the frequency. But 1 over t, 1 over the period equal to frequency. And therefore, v, the wave speed, equal to 1 over t becomes the frequency. We get the wave equation, a very important equation. Wave speed equal to frequency multiplied by wavelength. V equal to f lambda, and this is called the wave equation. Don't forget this. Speed of the wave is frequency of the wave multiplied by its wavelength. Let's now talk about two types of waves: transverse and longitudinal waves. Now, if the particle vibration is at right angles to the direction of propagation of a wave, that type of a wave is called a transverse wave. Now, let me see if I can show a transverse wave. I don't know whether you can actually see this. I have a spring that I have on the table here. Now, if I pull the string and look at this, what kind of wave am I generating? The particles are set into up and down vibration. Particles are set into up and down vibration. The energy moves at right angles to it. Now, this is the same kind of wave we generated on this spring, if you watch this one. Now, what I did here is I pulled the particle so that it is set into vibration up and down. Look at this. The particle is set into vibration up and down, and the energy goes along the length of the string. So if the particle vibration is at right angles to the direction of propagation of a wave, it is called a transverse wave. So when the particles vibrate up and down, you see, this is the particle, this is a segment of the spring that simply vibrates up and down, and the energy, the wave propagation, is at right angles. When the free end of a stretched slinky is given an upward jerk, the segments of the slinky simply vibrates up and down, and the energy moves at right angles to it. This kind of a wave is a transverse wave. Don't forget that. I will ask you this as we go on. Now, if the particle vibration, on the other hand, let me show you another kind of wave motion. I'm going to bring back my same slinky. Can you watch what happens when I set the particles? Now, I'm going to set the particles into left and right vibration. Look at this. Can you see what happens? When I set the particles into left and right vibration, the energy gets passed on along the length of the string. That means the vibration of the segments and the direction of propagation of the energy are both the same. So this kind of a wave, what's this again? This is a longitudinal wave. So what is a longitudinal wave? In a longitudinal wave, the particle vibration, the direction of particle vibration, and the direction of energy propagation are the same. Alright? So you must be able to distinguish between a transverse wave and a longitudinal wave. So if the segments are vibrated back and forth on left and right, the energy gets propagated to the right. This is the wave propagation, and this is the direction of vibration of the particles. If the segments of a stretched slinky is given a brisk push forward, you will see regions where the segments are crowded and regions where they are farther apart. Now, this is a characteristic of a longitudinal wave. There are places where the segments will be crowded. Look at this. And there are places where the segments will be farther apart. Now, the energy of vibration is propagated along the length of the slinky, forming high density. Now, this is a high density region, and the place where they are separated is a low density region. Alright, let me see if I can show one example of this kind of a wave. Now, if you watch here, these particles are set into left-right vibration by the movement of this red rod. Now, if you watch any of these particles are simply vibrating left and right, and see what happens. There are regions where the particles are crowded together. There are regions where the particles are further separated, and this is the characteristic of a longitudinal wave. A longitudinal wave. Alright, let me see if I can show you another illustration and how we can distinguish between a longitudinal wave and a transverse wave. Now, in this demonstration, we have the distinction between a transverse wave. Now, what's the motion of this red particle? It simply moves up and down, and look at the wave profile. The wave gets propagated that way. This is a transverse wave. A transverse wave has, now you got crests and troughs. And look at the longitudinal wave. Again, watch that red particle. This red particle simply moves left and right. You see that? And the energy gets propagated along the length. And in doing so, particles sometimes get crowded together, sometimes they get separated. So you get regions of high density and regions of low density. So the characteristics of a transverse wave is a transverse wave has crests and troughs. Crests and troughs. Whereas longitudinal waves have regions of high density, regions of low density, which move away along the medium. Alright, I want you to distinguish between a transverse wave and a longitudinal wave and see how the distinguishing characteristics are. A transverse wave has crests and troughs. A longitudinal wave has regions of high density and regions of low density. And we will continue. I'm going to record another part of wave motion as a separate part, and I will see you for that a little later. In the meantime, please look through and understand the basic mechanism of wave motion. You must understand the terminologies associated with wave motion because we're going to use it. So do the homework and make sure that you understand these basic concepts.